to me on the Rock, BCN.
Club to Dennis over at Whitehead Canton, who consented to put butter on our muffins. Dennis, thank you very much. And this is for you and from all of us on WBCN, including Smat. Right, Smat?
Thanks, Dennis. I sure am hungry.
Miss me. I know you miss me.
On the Rock.
I know you miss me, but love.
So here we are talking about the little FM-88K Elenco. I think some people would like to know how this thing works. It's actually got two integrated circuits. One integrated circuit comprises the radio portion. The other is the audio amplifier. So, you know, people build these little radios for different reasons. Maybe it's your scout troop, or it could be a project for your ham radio club, or maybe it's just something that one of your parents wants to show you. It might be something for school, a science project. But there are some people that want to know how it actually works. What's inside that IC? How does this radio actually operate and detect the stations and amplify the stations, and we can hear the stations coming out of the speaker. So in this video we're going to go through the actual operation and theory, and we'll do it in a simple way so that we understand how this radio actually operates. So first we need to talk about FM broadcasting in general. As you know, the FM band roughly goes from 88 to 108 megahertz. And of course, FM has been popular probably since the 50s. A lot of different receivers have been developed for FM, including car radios and everything from personal Walkman to boom boxes have been developed to pick up FM because of the higher fidelity that's available with FM. Instead of just handling 5 or 6 kilohertz of audio bandwidth in a monaural way, FM can handle out to 10 or 15 kilohertz of bandwidth, so you get high fidelity. The history of FM goes back to the 30s with Edwin Armstrong, who was really the father of radio. He invented the super heterodyne receiver and also FM. And in the early 30s he had some experimental stations going, and he experimented and convinced the Army to use FM as a major factor in World War II, especially for armored vehicle type communications, where the wideband FM was very immune to jamming from the Germans. Next we need to discuss how you make FM, and really FM is an audio signal that's applied to a transmitter that allows you to change the frequency of the transmitter in step with your voice or with music. So if you look at the diagram that represents an FM transmitter, you'll see there's an audio signal, usually from a microphone or a console, followed by some amplification and some compression or limiting so you don't over-modulate. And then there's a way to actually make the frequency change with frequency modulation right in step with the modulating wave, which is usually your voice or music. Next, you need to go on the air with a signal. That means you need a transmitter. The transmitter could be a $50,000 box, or the transmitter could be as simple as a few transistors. Here's a small transmitter that uses some audio amplification. Here's an even simpler one where it's just one transistor to make the FM. So what are we actually doing when we modulate an FM carrier? We're taking a carrier that at rest is at a center frequency. That frequency might be 87 megahertz. As we apply the audio, the frequency will go up and down with the modulation. So both the frequency of the modulation and the intensity of the modulation are going to change the waveform in such a way that even though the power appears to remain constant, the frequencies change right in step with the music or the voice. This is an interesting effect because most noise that's in the atmosphere and most noise made by vehicles changes in amplitude. And since FM doesn't respond to amplitude or doesn't employ amplitude as part of the process, it can reject those noises very effectively. This is especially important when you're talking about high noise environments. AM, as you might remember, picks up noise, ignition noise from cars, noise from motors, different types of electronic devices in your car, and FM is easily able to reject those noises. So what does FM actually look like? Well, since RF is invisible, it doesn't really look like anything. But if you were to be able to look at it, as with an oscilloscope or with a spectrum analyzer, the oscilloscope looking at the time domain frequency response of the FM, and the spectrum analyzer looking at the frequency domain representation of FM, you'd see that it's related to the modulation frequency and the modulation intensity as to how wide the signal actually gets. When the FM band was originally planned, they knew they wanted to do high fidelity transmissions. So they made the bandwidth, or the channel width for each channel extremely wide, approximately 200 kilohertz between each channel. Now compare that to the 10 kilohertz of a normal AM signal, and you'll see that they were very, very generous with their band plan. The band plan is roughly 100 times greater than the plan for the same number of AM channels. So you guys all still with me? We got to go over a few of the receiver aspects next. We just went over some of the basics on the transmitter. AM. Noise, right? AM. FM, no noise. Something to remember. AM has noise. FM is able to reject noise. Next thing we're going to talk about is the stages of a radio receiver to pick up FM. We need to take that beautiful FM that we've transmitted, and we need to now receive it. So we're going to be working on that next. So before we get into discussing the 7088 IC itself and all the parts that it's replacing, all of its stages, we need to understand the basic elements of an FM receiver. FM receiver is like any radio. It has parts that allow you to tune in the frequency, and that's the front end converter. You've got the super heterodyne principle in operation, where we're taking usually a higher frequency and converting it to a frequency that's easier to process or easier to filter. Usually that's a lower frequency. So the difference signal usually we're using for FM. Let's say we want to make a 88 to 108 megahertz receiver, and we want a 10.7 megahertz intermediate frequency. Very common. We would use an oscillator that tuned between 98.7 and 118.7 to produce that intermediate frequency of 10.7. That 10.7 you can see is a mix of the RF input frequency and the local oscillator, and we're using just the lower frequency content. Here's an old-fashioned tuner from the 70s and early 80s used in FM circuits. Next, you need to amplify and filter the signal, and we use the intermediate frequency amplifier that contains RF transformers that tune to 10.7. By using 2 or 3 of these in cascade and amplification, we can now select the frequency we're interested in while rejecting the adjacent channel interferer. Next, we have to turn those frequency deviations into audio. So we're essentially amplifying and clipping in a way that removes noise and extraneous signals turning it into a limited FM. Then we have to take the changes in frequency and convert them into voltages, specifically audio voltages. You can see in this discriminator, one would be tuned to the high side, one to the low side. Here's another style discriminator. Again, these turn frequency changes into voltages that we call audio. Automatic frequency control allows us to stay on frequency, and it's kind of a negative feedback system that allows the local oscillator to stay on the channel that you've selected. So finally we have our de-emphasis and audio amplification. What is de-emphasis? There's this interesting thing in radio called signal-to-noise ratio. This is true of audio or RF systems. Generally, higher frequency in an audio system, like imagine an LP record, is where you have a lot of hiss and noise. It's hard to reproduce high frequencies like cymbals and violins and so on. So they put this curve that actually increases the amplification at higher frequencies. And this has been done for quite a while with FM. And then you have to undo it on the other side and bring that added amplification back down to equalized or level audio. The audio is amplified inside the FM receiver conventionally with an audio amplifier. This is a mono push-pull amplifier that you find in many of the transistor radios of the 60s, 70s, and 80s. So in review, we have the front-end tuner or the mixer or converter, the IF amplifier, which includes filtering. We have some form of amplitude limiting, known as a limiter circuit, the FM demodulation. The demodulator basically takes the frequency excursions of the FM and turn it back into a varying voltage or amplitude that we can hear. And then finally we have the speaker itself, or the way we're listening, headphone speaker. Let's look at the inside of a vintage pocket radio. This is actually an AM/FM radio, but you can see the FM portions. You can see the converter, the IF amplifier, and the tune transformers, and then the little push-pull audio amplifier in the upper right-hand corner, which uses two transformers. One of the most important things that we need to realize when we're talking about integrated circuits is replacing a lot of these very expensive components. I say expensive. Those IF transformers probably cost something like 10 cents each, but when you multiply 10 cents times several of them times 500,000 units produced. So the question comes back to why do we even need to reduce the price? Why would we need a chip to replace components? Let's look at a few of the components that are used in that typical AM/FM pocket radio of the 1970s and 80s. Okay, let's take a peek at some of these components. Now when you look at the AM/FM radio, the things that kind of stick out really quick are this tuning capacitor. And that's a precision built piece right there, that tuning capacitor. Older tuning capacitors look like this. These are expensive to manufacture. All of the IF transformers, a lot of large electrolytic capacitors associated with the audio stages. This radio is so new, it does not contain the audio transformers that the older receivers did in the 60s and 70s. By this point in the 80s, they'd actually started to use different topologies that eliminated this expensive audio transformer. But we're still using a lot of transistors, resistors, capacitors. There's a speaker in here. One way to reduce cost, of course, is to replace the speaker with an inexpensive headphone or these cheap headphones. Some of the higher end FM receivers use tuning meters. If you can replace a tuning meter with light emitting diodes, that's a win. The variable capacitor itself can be replaced with a tuning diode called a varactor. These are all ways to reduce cost. if you use a potentiometer, which is your volume control on this receiver, and use that in association with a tuning diode, that's a much less expensive solution than using a variable capacitor. If you can completely eliminate the potentiometer and instead use push-button switches to tune the diode, well, that's even a larger cost reduction. So these are the reasons. Even though the part count on this radio probably, including the manufacturing, was less than $10, when you multiply that by 500,000 units, you're talking about real money. And they really desired to reduce the cost of these entertainment type receivers as much as possible in order to increase the profit margin. By the 1970s, the large-scale integration wars had really started in earnest, and a lot of players were out there competing for market share. As you can see, Signetics was just below Motorola and National. Philips saw this as an excellent opportunity to buy into the business in a bigger way and take more of the pie, and they purchased Signetics and all of their linear integrated circuit technology, including the 555, 565, 567, and so on. So the goal of building a single chip radio was really going to be important for Philips, and they put a lot of technology into developing some new single chip radios. These radios all came from Silicon Valley radios, the grandfather chip being the CA3089, and replacing all of those parts we talked about on the table with 100 transistors in an integrated circuit makes a lot of sense, because integrated circuits, even if there's hundreds of transistors, it's like printing t-shirts. You just keep making them and putting them in packages. It was a pretty good chip. It had all the IF amplification, had this new technology called a Quadrature detector for FM, and gave you just about everything you needed to make an FM receiver. The 3089 was a pretty impressive chip. So the CA3089 was quite an IC, and it shows up in a lot of commercial equipment. This is a satellite receiver board from about the mid-1970s to about 1980 vintage. And right in the middle is a 3089. The chip begins to show up in ham literature around 1972. Here's an article on using the 3089 in a 2-meter crystal-controlled receiver. And I know I was excited about this to the point where I actually ordered the very special 10.7 megahertz filter that was in the article. And this is that filter. I think I paid $10 for that back sometime in the late 70s to build that project. That project also showed up in the 1973 Radio Amateur Handbook. So the chip was really a groundbreaking leap forward in integration. So the RCA CA3089 brings a lot of great ideas forward, but you still need an FM tuner. You still have to have some selectivity, so that means a ceramic or crystal filter. You need some audio amplification. It's not a complete radio. Tuners do improve some, and we have some electronically tuned front ends that arrive. One of the big leaps forward with the 3089 is the Quadrature demodulator. This is a very nifty FM demodulator detector that can be put in chip form. It just requires one tuned circuit outside the chip to get FM. Basically, you're using a phase change with the FM deviation and comparing that to the unchanged phase, and you get the audio out. But you still got to tune something accurately to make it work. These new ideas went into the TDA7000, which was a true single chip radio that came around 1980, 1981. Philips introduced this chip Basically all you needed was an audio power amplifier and you had a complete FM receiver. Still required a tuning dial, variable capacitor, but much of those cans, much of the tune circuits that we're worried about are gone with this chip, and it makes a much simpler radio. So no more tuning. The chip basically reduces the radio, gets rid of the variable capacitor completely. All of the networks are greatly simplified. The way we got rid of the quadrature coil tuning is by using something called an all-pass filter, which is something that could be put on the chip. And we want to replace those ceramic and crystal filters as well, because they're expensive. And you can put active filtering on the chip. Low-pass active filters are a really great way to handle filtering your IF, but the only problem is they only work up to about 100 kilohertz, especially at this period of time. And the FM transmission is plus or minus 75 kilohertz. So you need a way to reduce that deviation enough that you can fit it into the 100 kilohertz bandwidth that those op amps can do. And the way that we do this is through something called deviation compression. It's a really cool idea. You look at the simple super heterodyne circuit, which brings in the 88 megahertz, for instance, at plus minus 75 kilohertz, and you have your LO there at 98.7, and you get out your 10.7, and so on, conventional. So the next thing we do is we bring that demodulated output back and modulate a diode that's connected to the LO, essentially FMing it. So we're making FM in the opposite direction, plus or minus 60 kilohertz. So when you add it all together, you end up reducing the deviation from plus or minus 75 kilohertz to plus or minus 15 kilohertz. Thus, the chip is artificially reducing the deviation enough that the simple op-amp circuits work. It's a very clever system. So, easy peasy, right? I told you it wouldn't be that hard. Actually, I guess I lied a little bit. We had to go through a lot. Had to go a lot of the foundational material on FM in order to approach the FM-88K in any decent way so that we could kind of know what we're talking about as we go through the circuit. You know, all of these stages that are inside that chip are really nice to look at in a big block diagram. But when you're trying to figure out what each part of the chip is doing, it gets a lot more complicated. So this kind of exhaustive treatment wasn't able to go in, really deep, but we got started at least. So why the diode in series with the LED? Actually, you get a couple volt drop on an LED, and you get about a half a volt drop on a diode. So that's a very clever voltage regulator. The chip only needs 2.5 volts to work, and the two diodes in series provide a poor man's regulator. Then we have the radio front end, which is an untuned front end. It's just a coil and a capacitor. You can squeeze the coil to tune it, but that's it. It's just a broad front end that covers from 88 to 108. So then we have some IF filtering, and like I said, with the reduced deviation, we can do that with op amps. So those IF filters and amplifiers are part of the chip itself. Next we have the IF limiter. We know that the limiter increases the signal enough to get rid of any noise that might be riding on the FM. Then we go into the demodulator. So the audio and muting circuit and the AFC are all associated internal to the chip, and the audio coming out is going through a potentiometer, and that goes into a very common LM386 amplifier, which runs on 9 volts. And 9 volts is fine for that chip, but not fine for the 7088, so we needed the two diodes for the regulation. So this tuning circuit I want to get into a little deeper. First, let's realize that the chip basically is running on 2.5 or 3 volts, and that all of these lines represent the 3 volt bus. So that's our starting point. Now, pretty soon we're going to hit that reset switch to the lower left. When we do that, it's going to bring that 3 volts up to the diode. So essentially, you're presenting 3 volts on both sides of the diode. Guess what? That equals 0 volts effectively across the diode. And when a varactor diode has no reverse bias on it, or 0 volts, its capacitance is actually at its highest. So when we build our ramp to tune the diode, we're actually going to start at a high voltage and go to a low voltage so as to lower the capacitance and tune higher. So to tune higher, we actually need a negative going ramp. We need a ramp that starts high and then goes low when we hit our run switch, or our tune switch, or our scan switch, whatever you want to call it. We want to bring that lower in voltage. Now, sooner or later, we're going to get a strong station. The limiter is going to supply a strong signal, and that detector is going to send a signal into the summer. And we're going to start to get audio, and that's going to send a signal into the summer, and that is finally going to reset our tuning and hold it. So once we've held it, basically the AFC keeps you on frequency, which is internal to the chip, and it will not change channels until we hit scan again. Now at the same time that we're stopping our scan and holding the voltage on the bottom of that varactor, we want to open up our audio channel. We want to unmute it, and cleverly all of this happens at the same time. So as soon as the thing finds a station, it stops tuning, it unmutes, and you get the audio out. It's a very, very clever system inside this chip, and well beyond what I could explain in a way that makes sense. I'm going to assume that we've covered the chip in kind of a historical way. Maybe went a little too far with it, but there's a lot going on in that chip. A lot going on in a 1-chip radio or a 2-chip radio. And we're talking about entertainment ICs, and entertainment ICs are made to be inexpensive. So can you be successful with a chip like this today, doing monophonic audio? It's not even a stereo. And the answer is only if you're using the chip in a very novel way, like a novelty radio, like you would put in a dollar store or a pound store, as they call it, or when you're making something like the Elenco, where you're just teaching people about radio. But there's not a lot of places where this chip actually can be used today in a practical way. It's mostly in toys and novelties where you're going to find this chip. So the end of the purely linear analog era has occurred, and today we would do all of this digitally, and we wouldn't be using analog large-scale integration chips from the 70s, 80s, and 90s, except when it comes to small radios like this. That's the only place where they're showing up nowadays. Hope you enjoyed this video, and we really got to do one more video on this thing. I'm going to call it Pimp Your Elenco. I call this next video Pimp Your Elenco. We want to take it out of this little world of a 2-inch speaker and pump up the volume, and make a real radio out of this.